Well, hello everyone. I'd like to share with you some work that we have been doing on trying to characterize the massive black hole mergers that Lisa will see. So this was work done using cosmological hydrodynamical simulations, and the idea is to try and find the optimal way to use simulations to cover the parameter space of interest for Lisa. Now, when we want to create a sample of simulated black holes, what we want is variety first. We need a statistical sample with many galaxies. In particular, we want the galaxies that host the black holes that are relevant for LISA. LISA can detect black holes with masses between 10 to the 4 and 10 to the 7 solar masses. And you see here that since black hole mass scales with galaxy mass, this means that we have to focus mostly on low mass galaxies. This is the opposite of what happens when you look for gravitational waves from plasma timing arrays. In that case, you're sensitive to more massive black holes, 10 to the 8 solar masses and higher, and so mostly large galaxies. So this sets the first constraint. The simulations that cover the black holes for LISA should include low mass galaxies, what we typically call dwarf galaxies. We also need to resolve small physical scales. This is because the physics of black holes is typically characterized by small scales, sub-parsec or so. Now, this is a clear challenge because when we think of simulations, they have the same constraints that observational surveys have, in terms of what we can do with our computational time. So we can have either large and shallow. So in terms of analogy with observation, something like this low energy size survey. So this would be a large volume simulation with many, many galaxies, but at a lower resolution. And this will not be able to resolve dwarf galaxies, but only the massive ones. Like in shallow surveys, you only see the bright sources. Or again, analogy with observations, you can have a small and deep survey. Think of the Hubble deep field or the Chandra deep field. In this case, you have a small volume, you have fewer objects, but you can have high resolution and you can see and you can model small objects. Again, in analogy with observations, this would mean that you can detect faint sources. So we have to find a way to benefit from what we can do with computers, knowing that there are these challenges of not being able to have extremely high resolution on an enormous volume. So what we decided to do was to combine two simulations. One is a very large simulation. It's called the Horizon Agent simulation. It's one of these large volume simulations. You may have heard of this, or Illustris, or the Eagle. They cover a large volume of the universe. So they include voids, they include clusters, but they have a limited resolution. So they don't resolve dwarf galaxies, and they also have a physical resolution of a few hundred to 1 kiloparsec. So we don't have the details of the gas and the stars near the black holes. But then what we also used is a resimulation, which is called the New Horizon, inside the Horizon AGN. So you see here, we took the volume of Horizon AGN, and inside it, we put a lot of effort, a lot of resolution in a smaller volume, a sphere of volume of radius of 10 kiloparsec. And by adding lots of resolution there, you see how we were able to increase resolution to about 35 parsecs. And at this point, we can see the details of gas and stars near black holes. Now, this simulation was designed to study black holes with high detail. So we've included also black hole spin evolution on the top of black hole accretion and feedback and dynamic refraction. And so we can use these two simulations to try and cover the parameter space covered by the black holes we will see with LISA. So I performed the analysis. And here I just report the distribution of the emerging black hole masses that we found in the two simulations. So you see here at New Horizon, the small simulation inside the large simulation Horizon Gen has mostly low mass black holes that cover perfectly well the range of masses for LISA. On the other hand, the large volume simulation covers mostly massive galaxies and massive black holes. You see here 10 to the 7th mass and higher. So it's only barely compatible with LISA, and it will be mostly useful for making predictions for cluster timing arrays. So this really shows how complementary of the simulations can really cover the parameter space for all gravitational wave instruments for massive black hole physics. On top of just having the simulation, we also have, in the case of black hole mergers, to pay attention to the physics of black hole mergers, which is more complex than the physics of just galaxy mergers. Besides, having the universe, creating all these galaxy mergers and having galaxies merge, the fate of black holes depends on additional physical processes. Dynamical friction that brings the black holes to form a binary, and then additional processes led by gas and stars that bring the black holes to where gravitational wave emission becomes efficient, and the black holes actually coalesce. So let me say a few words about how we model dynamics. Dynamical friction is a force that is long range, but is mostly sourced by material close to the black hole within a few parsecs. Now, most simulations have a resolution that is unfortunately lower than this. And New Horizon, which is one of the highest simulations, say, with such a large volume that we have, has a resolution of 35 parsecs. So even that is not sufficient. So we have to find ways to correct for the unknowns in the simulation. In literature, there are two approaches. One is to move black holes to the center of the galaxy just by hand. And the second is to account for the missing dynamical friction. So calculate the force that the black holes should feel if we had this higher resolution. And the second, so account for the missing dynamical friction, has been our choice for many years. See the papers by Michael Tremel and Hugo Pfister, showing that we have that black holes sometimes merge and sometimes don't, just following the way the potential well evolves. On top of this, as I said earlier, there are additional physical processes that happen on very sub-parsec scales. So this is after the formation of the binary. These are scattering with stars, immigration and circumbinary disks that remove energy and momentum from change the eccentricity as well of the binary until it reaches the gravitational wave-driven regime. Now, these are at the moment beyond the reach of our simulations, and so we include them in post-processing just using analytical techniques. So let me show you here the merger rate of black holes that we find. For the two simulations, the large one, Horizon Gen, and the small one, New Horizon. Now, if we just focus here on, say, the red curves, which is the final merger rate that we estimate once we included all the dynamical delays, you see that the small simulation has a much higher merger rate than the large one. Now, recall that New Horizon is resimulated inside Horizon Gen. So it's not a different patch of the universe, it's a patch of the universe included in Horizon Gen. So why much higher merger rate? This is because in New Horizon, we resolve dwarf galaxies. We have dwarf galaxies there. The dwarf galaxy holds the low mass black holes. And since in the universe we have many more low mass galaxies than high mass galaxies, the merger rate of galaxies is dominated by the dwarfs. And so this explains why we have more mergers. Now it's a bit more subtle than this. You have more dwarf galaxies than massive galaxies, but if these dwarf galaxies didn't host a black hole, well, you could have lots of galaxy mergers, but no black hole mergers. So the key point here is that dwarf galaxies indeed host black holes. This is now being shown also observationally. See the review by Jenny Green here, showing how many galaxies host the black hole as a function of galaxy mass. And also in the simulations, we find similar results. Dwarf galaxies with masses below 10^9 solar masses do host black holes. So when two dwarf galaxies merge, there is a non-zero probability that we have a black hole merger as well. So this really proves that resolving dwarf galaxies as and their black holes is crucial if we want to have a correct modeling for LISA. So when we looked at the galaxies that hosted black hole mergers, we addressed the question that is often asked, which is, are merging black holes found in merging galaxies? Now, my gut feeling was no, because there is a long dynamical delay between the two. And so we looked into this more quantitatively, and indeed we find that the time between when the black holes merge and the galaxy merge, this is shown here as a y-axis, a function of galaxy mass, is typically very long. It can be 1 billion years to about 10 billion years once we include all these dynamical delays that I discussed earlier on. So black holes merge after the galaxies have merged, and at that point, the appearance of the galaxy is not related to the merger that gave rise to the two merging black holes. Although you can have many, in 10 billion years, you can have many, many more black hole galaxy mergers. So the appearance of the galaxy is related to their cosmic history and not to the fact that they're hosting a black hole merger. So, my point here is that when we want to model black holes for LISA, we have to account for the galaxies that are important for this, and in particular dwarf galaxies. And so I showed you how using a higher resolution simulation, we could do that. And then we recover mergers that would be lost and missed in using simulations that are not as well suited. Then I show you here the history of two black holes from the merger that led the two black holes to find each other in the same galaxy, to when the binary forms, this is about 2.5 billion years later, to when the black holes merge. And this is 6 billion years from when the initial galaxy merger happened. So it's a long journey, but we can follow their evolution over time. And it's very important if we want to understand what are the type of galaxies where we will see LISA finding emerging black holes. So thank you very much for listening to me.